Okay, so we're live. We can just start.
Okay.
We already have some people in. We're going to be waiting for some 3-4 minutes, so everybody is joined and connected.
Okay, so YouTube is working now.
Mm-hmm.
Perfect. Here's the chat.
Yep. We've got some attendees connecting.
Do we have the list here?
Yeah, sure, it's on the right.
It doesn't appear.
Never mind, I can see them there.
Okay.
So yeah, for everybody who's just entered, we're just here on hold for some 2 minutes, so everybody joins and everything is connected, and then we're going to go ahead. Yeah, so I think, Guillaume, we're good to go. Maybe you want to do a brief introduction about you and NeuroTechBCN, and then maybe introduce Viktor and start.
All right.
Let's go.
So thank you everyone for assisting in our meeting. We are NeuroTechBCN. We are one of the chapters from NeuroTechX, which is an international organization for introducing neurotechnology to community, the general community, not just NeuroTechX, neurotechnologists, but also whoever is interested in technology. So today we have Viktor Tóth, who is a researcher. He's in New York, but comes from Hungary. He's preparing a design based on his work he's been doing, and basically, as it was exposed in the announcement of the presentation, he intends to create a platform in which mice can control with their minds a virtual environment. We will see the presentation, how it's going to be developed technically, and at the end we can also have a discussion on the implications and what's going to come after this. So yeah, we have 2 minutes to go. I don't know if Viktor, you would like to talk about anything. What do you like to what are you working right now on?
Yeah. No, I can start the presentation and
yeah, sure.
So yeah, thanks for the introduction.
Okay, so we're gonna I'm gonna mute myself, and the floor is yours, Viktor.
Nice, thank you. All right, I'm gonna put this here. So hey everyone, I'm Viktor. It is actually Toth. It's not Toth, but never mind that. So today I like to present to you how to train rats specifically to play Doom, and then somewhat generalize this idea so that we have a how on how to implement a virtual environment for rodents. Now, before I start, I'd just like to say this is a proposal. It hasn't been done, but I like to convince you that I like to take this problem into small pieces and convince you that all those pieces are possible to implement, and then we can assemble the whole thing together and say that it's actually not that difficult. Okay, so the idea itself is that you want to train rats to play Doom, not just by moving in the virtual environment, and I'm going to go that in detail, but only by mind control. And that is, I think that's the interesting part. So yeah, about my background, I studied computer engineering back in Hungary and then continued on studying neuroscience, specifically focusing on brain imaging at Aalto University in Finland. I mostly worked in software engineering and data science positions. Right now, I'm a research associate at the Feinstein Institute in New York, and we do all kinds of signal processing, like physiological analysis of physiological signals like heart rate, or EEG signals, ECOG, axonal recordings of peripheral nerves. We do all kinds of computer vision, and we develop clinical prediction models for the hospital system we are under. I have so I have background in neuroscience, in software engineering, and in machine learning, and I really like and also in parallel computing, programming GPUs, programming clusters of computers, and some game development background. So that's out of the way. Now, what is the motivation? Why do we want, besides it being I guess a cool thing to do, why would we even care to train rats to play video games? Now, one motivation is that what you can see on the right, it's the Morris Water Maze task. It's a well-established neuroscience or like behavioral experiment where the rat has to find the platform in the water. Now the problem is that, as you can see, rats don't really realize that the only way to not to suffocate in the water is to stay on the platform. They want to go for the human, they try different things. So the problem with behavioral experiments is that they require manual supervision. They require manual supervision from the experimenter, and the more complex the task gets, it's likely that the more supervision is required. And at one point, it's just when, like, for example, when you want to train an animal to play a computer game, and there's so many things that can happen in that computer game, you can't have someone, an experimenter there that just keep nudging the animal manually to do the right thing. So the idea here is that if you put the animal in a virtual environment and you're able to train the animal to play the game without manual supervision, then you can have a lot of exciting experiments. And even if you increase the complexity of the task that the animal has to do, it's still viable. So, okay, so let me talk about the how. So here's a simple drawing of a rat VR setup. I'm going to go into in detail like how this look like in a second. But for now, I just want an overall picture of what is the idea. So here you have a rat on a spherical treadmill. It's basically a ball. It can turn in all kinds of ways. You have sensors on the side of the ball, so you can translate the movement of the animal into in-game movement. You also have a water dispenser. So every time the animal does the right action, you give it a reward. Now, what are the actions, right? The animal can move around, and this is a simplified version of this shooting game, Doom, where you have a shotgun and you can move around and you can shoot. So for now, just for the sake of simplicity, these are the only actions that the animal can do. Now you can, by moving the spherical treadmill, you can translate that to in-game action. But you might ask, what is shooting? What is the action that the animal has to do, like a motor action, a physical action, the animal has to do to signal to the game that it wants to shoot? Now I'm going to go into like different versions of this, or like variations of how to what kind of behavioral actions we can use. But for now, let's just assume that if the animal nods, meaning it raises its head up, and we have a camera behind the animal, and we capture that the animal just raised its head, and that's going to be a signal to the game that the animal wants to shoot. So the next step is how are we going to give reward to the animal? Because the whole point here is the animal plays the game, and every time it does the right thing, for example, shoots the enemy, you would want to give it a reward to reinforce that behavior, and by doing that enough, the animal basically learns how to play the game. So from Doom, for Wisdom is a Doom engine. It's specifically created for reinforcement learning stuff. But what's important here is that Wisdom, you can extract all kinds of game states from Wisdom. So if so, you extract whether the demon has been shot, and if it has been, then you give some reward to the animal to reinforce that behavior. Now, even before you have rats in VR playing around, you can have a reinforcement learning model that learn to play Doom, which has been done a lot of times. Like it's not new. Reinforcement learning, it's a reinforcement learning neural network that learned to play in Doom on the side, and now it's just watching over basically the rat's shoulder. You know, it's just watching what the animal is doing in game. And I'm going to go into that in a second why that's central to this. So, okay, so let's go into the interesting part. So you implant a BCI into the rat in order so that you're able to decode what the intent of the animal is, right? So you can build a decoding model by recording how the animal is moving on the spherical treadmill, and also at the same time by recording its neural signals, and you can associate one to the other. So here you would take the neural signals and would decode, okay, where the animal, the velocity and acceleration vectors, you know, in which direction the animal wants to move, and whether the animal wants to fire. Now, now you can use this information and actually just detach all the information that's coming from the sensors that are on the treadmill, and use these decoded intent or to control the game. So that would be, you know, mind control. Now that's fine and dandy, but I haven't really told you how it is possible to train these animals in these complex tasks. So let's say you have a stimulation model, and let's say that stimulation model can stimulate, like this BCI. I want to be a little bit more specific. So this BCI is implanted into the motor cortex. Okay, it decodes, and this has been done before. It decodes, you know, in which directions the animal is intended to move. And let's say we can also stimulate the animal to contract its neck muscles, so to raise its head. So basically initiating the action of the shooting behavioral action. Now, and this is the this is the final drawing of this whole situation. So basically what you have is you have a reinforcement learning AI that you assume that can do the optimal action in the game. Now this AI at every step of the way can tell what is the next good action to make. Now, at points when the animal seems to be stuck, or it doesn't know, it doesn't seem to know that it has to shoot the enemy, or it has to raise its head to shoot the enemy, then the AI takes over for like a second or two, and then it uses the stimulation model to stimulate the motor cortex of the rat to raise its head to do the behavioral action. Now your decoding model is gets that information, and it understands that, okay, now the rat wants to shoot, and it translates that, it sends it to the game, and now the animal and now a demon is shot, and then the animal gets a reward, and this behavior is reinforced. So that if you do this enough, the animal will be able to learn that, okay, if I nod, if I raise my head, then that's an act of shooting, and I should shoot whenever there's something, you know, stimuli in front of me. That's like some moving object or a monster-looking object. So that is in a very abstract manner. That is the idea. Now, why is this interesting? And I promise you, this is the most abstract I'm going to get here. But as I said before, the motivation here is that rats are difficult to train on complex tasks. And what the combination of all these things, what the virtual environment, reinforcement learning AI, nudging the animal to do the right thing, and cortical, or more specifically here, motor cortex stimulation, gives you basically translates the problem of designing and implementing behavioral experiments. It renders it a software problem instead of a hardware problem. You don't have to, for example, you don't have to build a maze to start an experiment. The only thing you have to do is that you have to update the software, and then it's going to have a different environment in it. And also because we assume here that we can train an AI, a reinforcement learning AI, on the task, and a lot of complex tasks. Like you can, there's a lot of, well, reinforcement learning AI has gone a long way in the last, whatever, like 7 years. So it can learn very complex tasks. So as you increase the complexity of the task, the reinforcement learning is still with you. It can still, you can still have an AI that's able to do close to optimal actions in the game. And then through brain stimulation, you can translate that knowledge sort of with brain stimulation and with rewarding the animal for doing the right actions. You can translate that information into the rat. So with this, you can just design new experiments, and the only thing you have to change basically is the software, is the game that the animal is playing. Now, why Doom? So Doom came out in the 90s. It's been open sourced for decades now. There's a bunch of mods that you can have in the game. There's a bunch of different there's a bunch of different game mods. It's very low resolution, which also helps because the visual acuity of the rats, which I'm going to talk about, is very low compared to humans. So you necessarily want a low resolution game. And it's just really easy to change maps, to add new monsters, to script the game. So it is very, oh, and it's also pretty fast, which you do want, because there's a audio visual feedback that you want to give the animal. So if the animal moves on the spherical treadmill, you want the animal to immediately get a visual feedback on that movement, so that it understands that it's in some environment and it's moving in that environment. Okay, so let's see how the rats actually see this game. Like how far can the rat vision can take us? Because if we can, from first principles, if we can derive that, okay, the rat can actually see the demons, the rat can actually see the doors, the rat can understand that it's moving in a corridor, given its visual acuity, then we can conclude, or at least we can hope for that the animal can actually learn this game. Now, animals are colorblind. So you wanna, oh sorry, rats are colorblind. So you wanna remove the rat channel. Their cone to rod ratio in their retina is 5 times lower than humans. So this was sort of my way of like fixing that, but it's not completely accurate. it's somewhat accurate. So I reduce the color intensity to reflect that. And then rats have this 1 cycle per degree visual acuity, which means that if you draw 2 lines and those 2 lines are separated by 1 degree field of vision, then the rats are able to recognize those 2 lines as separate. But if those 2 lines are closer together, then the rats can't tell them as different lines. So here I applied some Gaussian blurring that basically got rid of the well, 90%, like technically it got rid of 90% of the lines that are within 1 degree distance. And well, I mean, this is also approximate, but if you would cover the 90 degrees of the rat's field of vision, then likely this is what the animal would see. Now, for those who are not familiar with Doom, let me play this video. I hope it's not going to be too loud. All right. So this was the first map of Doom 2 with like this rat vision, with like reducing the like blurring the image and just turning black and white for simplicity. So those who actually know Doom 2 understand that this was not the whole map, and this was actually the shortest path to get to the end of the map. But I think if the rat is able to go through this map while killing the monsters in the way, that would be the first milestone. Then you can, from there, you can pivot to like more complex tasks. All right, so let's see what kind of VR environments are out there for rodents. So usually these VR environments, they vary according to the degrees of field of vision that they cover, and also what kind of sensors they have, and how do they present the image. Is it through a screen, or is it through a projector and a mirror system? Now, what has been done in that actually? So I will not be able to cover all the rodent VR research. It has been going on for like 15, or maybe even, it's been 2001. It's like almost, yeah, it's been 20 years since these experiments are going, and there's a lot of different ones. But I like to cover like the more interesting ones. So, well, the least interesting one is rats have been, and also mice have been taught to run in corridors. And that is the simplest. It's just a linear corridor. The rat runs to the end, and it will get a reward when it does that. Now, why is this even interesting? Well, you can measure the place and the grid cells of the animal, and use that to basically have an understanding of the representation of the animal where it places itself in space. So for mostly, it's mostly used for those experiments. Now, there has been done like 2D navigation tasks that are a little bit more complex, because the animal not just running in a corridor, but it can move around on a 2D plane. And in this experiment, the rats had to run under these columns, and they had to run towards the south, so one direction. They had to figure out which direction it is, and they had to run through columns, and every time they did, they got a reward. I think this was a mice experiment where they made them select. It's a multiple choice selection task where you have surfaces colored in different different colors, and then the mouse has to approach the surface that's colored green. So it's a circular arena, and the mouse you just turn around and just find the right surface and just go towards it. There has been also done like VR experiments in more complex mazes. Like what you can see on the right is it's a circular maze, and it was like this experiment was done with gerbils, it's a kind of rodent. And what the animal had to learn is that, for example, if it starts to go from the left, then every time it goes over or touches those green patches, it gets a reward. So it learned basically to go in circles. It goes to the one on the left, and then one on the top, and one on the right, and it just keeps going like that. And what was the interesting about this experiment, and I will say this now, is that first they taught these rodents to run on a linear, on just a linear corridor, right? Run to the end, turn around 180 degrees, run to the other end, turn 180 degrees. So that was the first task that they told them to do. And once they learned that, they put the animal in these more complex mazes, and they instantaneously they recognized how to navigate in these more complex mazes, which is pretty cool. And also in these VR environments, there has been done like neural decoding of movement intent from the one that I'm citing, that's mice recording of the mice cerebellum to decode in which direction the mouse wants to move. Yeah, so there's pretty much a lot of things that have been done in these VR environments, and there are a lot of different VR environments to choose from. Now, so again, a little bit of abstract. So how are we gonna get to mind-controlled movement in the game? Also, this is not something that hasn't been done, but first you have a BCI, you have a brain-computer interface implanted, you record from the motor cortex, you also record the behavior of the animal using a camera or using the rotation of the ball. And at first, you only use the recorded behavior to drive the game, right? To initiate in-game actions. And at one point, this can be varied of how you actually do this, but you can start using your decoder as a source of action for the game, right? So you start getting rid of all the recorded behavioral actions, and you start to only use the mind control to do the game. I mean, you can do this gradually, or what has been mostly done is to just let's say train the rat to do the task, or like let the rat to do the task for an hour. You decode you're training your decoding model while the rat is doing that, and then at one point you just turn it off completely. You turn the information that's coming from this the treadmill, and you only start using the decoded intent to drive in-game action. So what are experiments out there that has done similar things? So so there was one experiment where they just recorded from one motor neuron, and they captured what is the firing rate of the motor neuron, right? And every time that firing rate increased to above a set threshold, the animal got a reward. And by doing this enough, the animal obviously doesn't understand this, but by doing this enough, the firing rate of that single neuron slowly started to increase more and more, so that the animal got more and more rewards And yeah, and obviously the animal doesn't understand that, okay, right now I have to increase the firing rate of my, motor neuron, I don't know, X to get some reward. But through reinforcement, they could do this. Now, also rats has been trained to pull or press the lever to only through mind control. So the experiment there was to, the rat has to pull the lever, and while it was pulling the lever, at the same time, the water dispenser was approaching its mouth, right? And it had to pull the lever to a certain amount of time so that it stops right in front of its mouth. And that, and after a while, they just completely turned off whether the animal pulled the lever. It didn't matter. The only thing that mattered is what they decoded from the motor cortex of the animal. And if they decoded that, okay, now I want to press it, and now I'm gonna or now I want to pull this lever, and I'm gonna pull this lever for I'm still pulling it, I'm still pulling it, and now I stopped, right? They could decode that, and at one point the animal started not really doing the physical action. And what I think is even more interesting is that they teach non-human primates to learn direct cerebral control to an actuator. So what you can imagine is that the monkey had a joystick in front of it, right? And if it turns the joystick to the left, it moves the cursor on the screen to the left. Now, what the monkey was able to learn, like so monkey was doing this task, right, for an hour, and it has to move the cursor in a certain point on the screen. So the monkey was doing this for an hour, and at one point they just turned off the input from the joystick, and they only use the decoded neural intent. And actually, the monkeys just stopped using the joystick altogether. And what was even more interesting is that their motor cortex sort of molded in a way to specialize to drive the BCI the right way. So whatever was, so in the beginning, there was a resemblance of neural activity, that what the animal would do when they would move the joystick. But at the end, whatever neural interface they built in their head, it was not similar to the original joystick movement neural pattern. So the animal was actually able to adapt to the BCI to move the cursor around. So yeah, so that's about movement, and we're gonna go into decoding and stimulation deeper in a second. So okay, what about shooting? Because in this experiment now, for the sake of simplicity, animal just moves around and can shoot. So what kind of behavioral action are you going to associate to shooting? There's a couple of options. Like the opening of the jaw. So in that case, you would have a camera in front of the mouse or the rat, and every time it opens its mouth, you capture that, and then you translate it into the in-game action of shooting. Or what I've mentioned, the head nodding or raising the head. You can do blinking. Blinking has a problem that the animal obviously, or the rats blink 5 times a minute already. That's probably increased if you put them in front of a screen. So that's that. Licking is another way to do it. So on these water dispensers, they usually put piezo electric sensors to record whether the rat licked the water dispenser. And while using licking to drive shooting is obviously a little bit confusing, because am I licking to shoot, or am I getting the reward through, so there's a discrepancy there that an animal has to go through. But I'm going to go into that later in the end of the presentation. And also vocalization. So rats can give out, I think, around 7 different, or like there's 7 groups of different squeaks that they can give out. and they have different meaning. You can actually stimulate, and that's what I refer to there. That's what I cite there. They can stimulate the rat to give out a certain sound, and they actually squeak on the 50. Well, they also, but they some of their squeaks are in the 50 kilohertz. It's around the 50 kilohertz, so we can't really hear it, but we can have microphones that can. And then the last option, well, before I go into that, so all of these, why did I select these ones, right? Now, there are multiple reasons. So one of it is they are fast. They're pretty quick actions, which we want to have there because when you brain stimulate the animal to do a certain action, and that certain action is temporarily, it's long, then you might get into the problem that your stimulation sequence is going to be complex, right? So in the beginning, just to simplify things, we want to have behavioral actions associated with shooting that we want to stimulate to be very short, very quick. It also reflects actually what the action, in-game action is. Shooting is very fast too, but the main thing is that if we want to start stimulating, let's start simple and let's start with short stimulation sequences. Also, I selected these as they have all been done, like the stimulation of all of these actions, motor actions, have been done in previous experiments. So it's nothing new. Now the last one, the auxiliary neural interface, and that's a little bit trippy. So, and there's not that much of a research on this one. So what I mean by this is, can you build a neural interface in the brain of the rat so that basically you don't have to select a behavioral action like opening of the jaw or nodding or all that. You can select a group of neurons that, let's say, should have a high enough firing rate to associate shooting with it, right? So at that point, you don't need the animal to do any kind of movement. You just somehow prime the animal to drive some of its neurons so that it shoots in the game. And again, I'm going to go into more detail that how that can be done, but again, that's there's not a lot of research on this. Okay, so in practice, how does it look like? So you have your AI, watching over the animal and like sees that, okay, there's a monster in like ahead, but it's not straight in front. So if the animal would shoot right now, it couldn't shoot the monster. So the AI understands that, okay, now it's the next action, the next optimal action to do is just to turn left. And again, just to further simplify this, the experiment, I mean, you don't even have to, because I would assume for you to be able to stimulate the animal to move on a treadmill, you would need a complex long stimulation sequence to initiate that. So even to simplify there and only stimulate when the animal has to shoot, we could have a servo motor and the wheel turning the treadmill under the animal to get into the right direction. And actually, this has been done in a previous experiment. The only difference was that they did it manually. So that was an experimenter there turning this treadmill to tell the animal, okay, you gotta actually move this way now, right? But if you have a reinforcement learning AI that knows what to do next, then it can just drive the treadmill itself automatically. And again, you don't need manual supervision. So, okay, so turn to the left. Okay, what's next? Now the monster is right at the front. So now it's time to shoot. So the AI instructs the stimulation model to shoot, which in this case means that the stimulation model stimulates the animal to nod, to contract some neck muscles. And then your decoding model understands that, okay, this was actually a nod, and sends a message to the game that now it's time to shoot. And because it was a successful shot, the demon is killed and reward is given to the animal. So this behavior is reinforced. So the animal understands when you move the spherical treadmill under it, right? It has to adapt to it, right? It has to move itself too. So it understands that, okay, now I'm turning to the left. I have to turn to the left. Now I have to shoot. And at the end, you just reinforce this behavior. Okay, let's get into the weeds. Neural decoding. So how would you go about the neural decoding of, let's say, movement intent from the motor cortex? And as I said, this has been done a lot of times. There's models built on motor cortex activity or cerebellum activity to decode the velocity and acceleration of the animal, the velocity and acceleration vectors, and also whether the animal intends to nod, which means that it intends to fire. Now, how do we do decoding from let's say Utah arrays? So you have those Utah arrays in there. It records voltage changes, waveforms, and then you recognize those waveforms as neurons firing, as different neurons firing, and at that point you can have what I drew at the top. It's a time series of and I'm simplifying a lot of things here, but to just get through this, you have a time series of neural spikes, and what you usually do is that you take some bin, you take, let's say, a 50 millisecond long bins, and in those bins you just sum, how many spikes each neuron had, and then this is what you call a spiking rate, and then you take these spiking rates and as input to different models, and then you predict whatever the animal intends to do. Now, you can have just very simple linear regression models that just takes like a history. Let's say, again, it takes 500 millisecond long history of 50 millisecond long bins, and it just predicts what the animal wants to do next. And if you have high bandwidth recordings from the motor cortex, you might be able to just do away with a linear regression model, and you don't need to go into more complex models like recurrent models, filters like the common filter, or recurrent neural networks like the long short-term memory, the ones that I brought up here. LSTMs usually work better than linear regression at least in some spiking rate decodings. They in previous experiments they've shown that it works better. It's in like there's some intuition why it works better. Common filters are basically just you can think of them as a linear recurrent learning model that also gives you uncertainty on its prediction. So let's say if you predict that okay, the animal is going 5 centimeters per second in this direction at 30 degrees, then common filter can give you a sort of uncertainty on that, saying that actually, I'm not really sure it's going to be 3 centimeters per second. There's also some likelihood of it being 4 or 2 centimeters per second. It can give you basically a Gaussian over the possible speeds and or velocities, and that might be useful because you want to use these decoding models at the point when you're sure that these decoding models work, right? And this can give you that. It can give you the uncertainty of whether the model actually knows that which direction the animal wants to move in at what speed. So what's actually easier about neural decoding is that you can have some recording of an animal playing the game, recording its neural signals for an hour or two. Then you can take all that data and you can offline train these different models. And even if you have multiple animals playing the game, I mean, I don't assume that this would be true, but even that is possible. Maybe some models work for some this offline. It's kind of that's why it's saying it's easy. You can try different bin sizes or different length of history. There's again a lot of research in this and best practices that you can apply. Now, neural stimulation. This is a little bit more complicated. So how would you stimulate the animal to nod, for example? Like, how would you start? And probably the first step is to look at the stimulation maps. So these were done in the 80s, where they stimulated different areas of the motor cortex of the rat, and then recorded whether the rat, what kind of muscles of the rat were moving. And you know, if you want the jaw to if you want to open the jaw, you basically can hone in on that area, that the purple area, and stimulate that to induce that behavioral action. So that's probably the first step to at least have an idea where you want to stimulate. And after that, you probably would want to train a control model on stimulating around that area, and that's what makes the neural stimulation part very hard. So you obviously can't do this offline, right? You have to stimulate the animal and you have to see whether the animal actually opened the jaw, right? And that's the only way how your control model can learn and optimize itself. So there are different ways to do this. And there's one example here, and I don't know how deep I can go into this, but this has been done to contract muscles of monkeys, and what they this Bayesian optimization. So if you want to search in the parameter space of stimulation, because that's the difficult part, right? Which electrodes to stimulate, in what sequence, and how much time there is between the stimulation of the electrodes, and what kind of waveforms you use to stimulate, and at what frequency you're driving those waveforms, and at what amplitude, and whether there's a polarity to it, whether it's bipolar or not. So there's a lot of stimulation parameters to cover, and probably you can have some assumptions that can reduce these. So for the example here, for just to show you like what can, like, for example, Bayesian optimization can do. Let's say the stimulation frequency and the amplitude and the waveform are all given, and the only thing you want to search is actually which electrode to stimulate. So on the bottom you can see well, a Bayesian optimization in action. So what happens is that you have a 2x5 electrode array, and you want to find the electrode that induces the muscle movement the most reliably, right? Because you can stimulate some electrodes and you might not get anything, because it's just because the animal is just in a brain state where that stimulation doesn't really mean anything. It gets inhibited subsequently, or something happens. So it's not completely, it's very stochastic. Now, that's what Bayesian optimization is good at. It's capture not just what electrode to stimulate at, but also what is the probability that electrode is actually going to give you the right response. So what you do is that, like on the left, they tried one electrode. So they tried different electrodes, right? And then they keep building this blanket, this distribution over the space of electrodes, the X and Y dimensions, right? It's 2 by 5. And on the V, or on the V axis, you see how much muscle response was recorded when a certain electrode was stimulated. And here you assume that there's some kind of smoothness between the electrodes. So if I stimulate, one electrode and I stimulate another electrode just beside it, then I'm going to get some similar responses. And that can be a hard assumption, it can be a soft assumption, depends. But here that's what's assumed. And as you sample this space of like, okay, I'm going to stimulate here now, I'm going to stimulate here, here. At one point, you get this blanket over the support of your stimulation space, and you get like which electrode gives you the most response. And what Bayesian optimization gives you basically is that you don't need that many stimulations to actually figure out what's the best electrode. Yeah, on the top right, I also have that's a figure of stimulating rats to give out a certain squeak. So again, it has been done. They found some areas that if they stimulate 400 microamps is pretty high though, but they found some areas that they can stimulate to make the rat vocalize. Now, stimulating the motor action as opposed to doing that auxiliary neural interface stuff that I mentioned has benefits and has some cons. So you can record the response to the stimulation, right? You can have a camera right in front of the animal, or you can have some piezo electric patch or something that records whether the animal contracted a muscle. And then you use that response to adjust your control model so that next time it will try to stimulate the right electrodes with the right stimulation parameters. It's also very well researched. So there are a lot of, as I said, there's these stimulation maps, you can use those. But the problem is that once you start to introduce more and more in-game actions, like now we just talk about shooting, but what if, we talk about like changing weapons, all kinds of things. At one point, you're going to run out of these motor actions. So that is a problem. It's also hardware dependent, right? So if I want to record the animal that it nods or it's opening its jaw, I need a camera to do that. If I want to add a new behavior, like blinking, well, that also can be done actually with a frontal camera. But you understand, like the more motor actions we want to include, the more hardware we need to jam into our VR setup. So what's the alternative? So there's not a lot of research on these. So I'm gonna go into the as deep as I can, and then at the end you can ask me some questions and we can figure out what more I know. But let's say you select just a group of neurons. You select a group of neurons, so just select a single. If you do intracortical microstimulation with a Utah array, you probably not even when you stimulate, you don't stimulate a single neuron. You stimulate thousands of neurons or even more. So you basically select, let's say, one electrode, and then and all the neurons around it, and then you stimulate those regions, and you also decode from those regions. And let's say you record from those neurons, and then you establish that, okay, the firing rate, the average firing rate, the baseline firing rate of these neurons is X. And then you set a threshold that's somewhat above X. And then you say, okay, every time the firing rate of these neurons exceed this threshold, then I'm going to translate that into a shooting in-game action, right? So every time those neurons raise their firing rates to a certain extent, you're gonna decode that as shooting. Now, what you can do to build a simple auxiliary interface is that you have the the animal playing the game, and there's a monster coming up, and you stimulate those neurons that you selected, and there can be a lot of there can be some problems here, but just stick with me. So you stimulate those neurons, and then you decode that, because you can see that the firing rate of those neurons increased. You can decode that as a shooting action, and straight after that you give a reward to the animal. So you reinforce the context dependent activity of those neurons, and the context being that there's a visual stimuli. There's a monster in front. So that's probably the simplest way to do this. Now you have a couple of problems here, because once you start to stimulate, you're going to have a lot of artifacts. And if you want to record from the same neurons that you stimulated, that's going to be ugly. So in the beginning, you might not even want to decode it. Every time you stimulate, you assume that the firing rate increased and that a shooting can happen. So there's no decoding happens in the beginning when the AI stimulates those neurons. But later on, when you see that the firing rate is increasing, then you can decode that without stimulation. Then you can start decoding that as a shooting behavior. Yeah, you can also do the other different things. So one problem you might can think of here is, okay, I stimulated some neurons in the brain. What if those neurons are not ready to be stimulated at that time, right? What if those neurons just inhibit each other, and at that point there's no information coming out from that circuit, right? It's just you stimulate those neurons, they inhibit each other, and it's just your stimulation just disappears, and there's no network effect. So there are ways to counteract that. I would propose that it's not really a problem, because just because how crude your stimulation, like ICMS, intercortical microstimulation is, you would stimulate so many neurons that has so many random inputs and outputs that I think at one point they're going to learn to have a higher firing rate, and associate that with shooting. But yeah, so that's that. Okay, so what is the rough action plan of training rats to play Doom? So there's an interesting idea. The first one is to first train the rats to play in a cardboard copy of map 01, and I'm going to show you what the map 01 is. What you see on the right, it's a Doom map. So you could build a cardboard copy of it. You can even have like some Arduino, I don't know, mechanics in there, so that every time you see that the rat is in front of a door, you raise the door, right? You can do all kinds of things. And this actually has been done in previous, in at least I've seen one VR, rodent VR research, where before they put the animals in VR, they let them run around in the cardboard copy, but I think they did not have a control, meaning I don't know if this actually works. I don't know if this actually helps, because in that experiment they just had like all the rats run around in the cardboard, and they didn't have a group of rats that didn't do it and a group of rats that did it. That wasn't the point of that experiment. It's something to try. I think it's interesting. Then once you had that, and you can put rats into this VR environment, and not even have them implanted yet. Just put them in the VR environment, figure out if those rats have different personalities that you can, well, I guess you can describe by saying personalities. So one would be more curious, one would be more lazy, and you probably want those rats that are high performing. So this could be some sort of like selection, like selection phase, when you have these rats just navigate around in VR and be instructed by the AI just to move around, not even to shoot. And you can see how good they perform. And from there, you can select the ones that are really good, and then only implant those rats, let's say with Utah arrays. And then after you have that, they are in the environment, they're playing, and you can decode. You can train your decoding and stimulation models while they do that. And first you just have the animal navigate around, right? And then you introduce the shooting behavior through stimulation. And at the end, you graduate the rats to the first map of Doom 2, which I showed you, and which is on the right side of this. So this is just a comparison of different mazes that has been used for rodents. On the top left, you have the Hampton Court maze. If you look at it, it's kind of complex. It has a structure to it, but it's kind of complex. So what I want to convey with this slide is that map 01 is not at all as complex as other environments, as other mazes that have been used before. So the spatial cognitive, the spatial memory of the animal doesn't have to be that crisp to play this game. So what you can see, what I painted in green on the right, is all the areas that the animal can get to without pressing a button or without finding any secret areas. And the red line represents the shortest path between the start to finish. And as you can see, it's really simple. Like if it's really simple. But if we can train the animal to play this map, then we can pivot from here and like have more and more complex tasks. So how would you do that? Again, we want to, in the first experiment, we just want to give all the information from the animal. We want to help out the animal. So we can create these different maps, a sequence of these different maps, and complicate them more and more as the animal is able to play or able to go to the end in the previous maps. So just make the maps more and more complicated. And what you can start with is a linear corridor, and then you can introduce what you can see on the top or the bottom right. You can introduce a 90-degree turn. So this, the very first map would introduce movement. It could introduce like very simple 90-degree turn, and also the exit door stimulus. And this is important because we want the animal to capture that there's always at the end of the map, and this is the same, using the same textures in the corridor, on the exit door, on the button, as you would see in the final map, as the animal would see in the final map. So the animal understands that, okay, that's the exit door. The exit door is very close to where I get the reward. So the animal, goes through the corridor, turns to the right, opens the door, bumps into the door, opens it, bumps into the button, and it gets a reward. So every time it sees the exit door, it understands, okay, now that's where the reward is going to be. And once the animal understands that, you can introduce more complex spaces. You can introduce, instead of corridors, you have these larger spaces where you have, again, the same exit door that the animal just has to look for, right? But then we understand that, okay, there's the exit door. Like I have to find it. There it is. I'm gonna enter, and then I'm gonna get my reward. You can add more complexities, random turns. So basically, you want to add more and more random turns so that the animal doesn't overfit on your map. Meaning, it doesn't learn to only play a certain map, but it's able to navigate in arbitrary maps. Okay, so once the navigation is working out, the animal can run around. Then you can start introducing monsters, and yeah, you can put them in random positions. At this point, your reinforcement learning AI doesn't even have to be. It doesn't even have to be a reinforcement learning AI. At this point, the only thing, because we can assume that the animal can run through these can navigate through these spaces. Now your AI, the only thing it has to do that it has to capture whether the animal is right in the is close to a monster, and then turn the animal towards the monster and then do the shooting action. Right, that's the only thing. So it's very very much as the first experiment. It's just very simplified so that we can be sure that it's going to work out. So yeah, so first these monsters can be stationary, they don't move, and they can start introduce movement, and then they can start attacking the rat. And if the rat get attacked, you can introduce some air puff in the rat's face as like feedback, which might, it's you don't want to complicate the rewarding scheme too much, because rats might get risk averse. So if they obviously if they get puffed in the face all the time when they see the monster, they want to run from it. They want to avoid it at least, and that's not the behavior that you want to encourage. You want them to shoot it. So there's some leeway here on how one could do this, but you have to look out so that you don't introduce highly risk averse behavior. Now, okay, let me, I don't know how much time do we have. Oh, okay. Let me fast go through these. So these are all the VR setups that has been brought up, has been invented or put together before. So this is the first rat VR setup. It has a 360 degrees view. The rat doesn't turn the ball to turn like to yaw, meaning that to turn to the right to the left. It doesn't turn the ball. It turns its own body on the ball, and then it can make the ball roll in wherever the rat is facing. It's in a metal half sphere mold. You have air. It's your spherical treadmill is air cushioned, so that it has some airflow coming from under, so that there's not much traction with the half sphere mold. Here the animal is body fixed, and yes, you have your optical sensors, cameras, and then you have this mirror system that projects the image onto this onto the screen. Now, okay, so this is one solution. This was the first one. You can see that it's kind of complex, and it's mechanical. Like mechanically, it's kind of complex. You can get a lot of things. You can screw up a lot of things, and yeah, it is what it is. So there's a commercial VR setup out there. They have different versions of it. They have this dome setup and this TFT array setup. And they have all the air puffs, the water reboard system, leak sensors, like everything is already inbuilt and it's been tested in experiments. Only problem is that it's mostly been tested with mice, not with rats. And the ball is pretty small. So if your rat starts to grow, and this might be a problem, although some could counteract that, but this might be a problem that if your training regime takes too long, your rat starts to grow, right? It's going to outgrow this 30 centimeter ball. And also you should be able to change these balls, because their mass should be 1.5 times the mass of the animal, so that the animal, when it exerts some force on this treadmill, it actually exerts the same amount of force that it would if it just walks on the ground. And you don't want to tire your animal too much, because then they can't play that much. So that's the thing. Okay, so for looking at these, what was the first one and what is a commercial setup? How do we, if we want to build our own, and I propose that we should, for this experiment specifically, how would you build a VR setup? What directives you want to have? You would have. So one of that is you at least need less than 100 millisecond response time. So if the animal moves, the audio visual feedback has to be under 100 milliseconds, and I mean, it should be actually under 50 or even lower. So it should be as low as possible, so that the environment looks somewhat real, right? So that the animal can understand. It only uses motion parallax to understand that this is a 3-dimensional space right? Because it's just a screen. It doesn't have 3D information. If the rats look like this, it's not like there's objects appearing from behind other objects. So it from the visual feedback, it understands that it's in the 3D space. So that visual feedback has to be very crisp. But that's possible. It's not that difficult. So then what I think is the most important is that you want to minimize the stress on the animal. And there's two different ways how you constrain the animal to stay on the treadmill. There are other ways too, but these are the main ones. One of them is head fixed and the other one is body fixed. When you head fix the animal, you actually nail in some sort of metal that you can attach to, and that doesn't let the heads of the animal move. And that takes, usually in these experiments, it takes a week for the animal to get accustomed to that. Because I mean, it's you can imagine if if they nail down your head, how annoying that is. And this usually have a reason why people do it. But here I would just, what I propose here is that you don't need head fixation at all for this experiment. You're good with body fixation. So usually why they use head fixation is to be able to record neural signals, like with patch clamp or with two photon imaging, where you can't have the head of the rat moving around. So that's one reason. The other reason is that that's more of a made up reason, is that they wanted to make the environment more authentic, and you can only make this environment more authentic by controlling the stimulus. So controlling what the animal sees, right? So if you have a 270 degrees visual coverage and the animal just looks to the right, then it sees some sort of black spot. There's nothing behind him. So is that going to ruin the experiment? Is the animal just going to, well, I'm not in the real environment. What am I doing here? But actually, what it turned out, and what you can see on the left, is that you can cover only 90 degrees of the visual field, and just present it on the screen, and it works. It works fine, and an animal can, and that's a mouse there. The mouse can move around in this 2D arena without any problems. So I think for this experiment, it's very clear that you don't need to head fixate the animal if you have a BCI that's either wireless or at least wired, and not and you can jiggle the wire around. That's not a problem. Right. So just to be quick here. So that was a PhD thesis, what you can see on the right, what I'm referring here, that has a much better setup than what the previous ones that I've shown you. And this one, like, have the ball completely out there, so you can put the sensors in there, you can put the wheels on it without any problems, and it's just a very simple setup. You don't even need a half sphere mold. It actually ends up being also more silent because of how the air cushioning is working in this design. Now, I want to even say that you don't even need like a 270 degrees field of vision, and you don't need to have like a tent around the animal to actually make it understand. Oh yeah, one thing I didn't say on the top right. Oh, sorry, the bottom right. That's another experiment where they covered 180 degrees of field of vision for the mouse, and they recorded from place and grid cells, and the recorded neural activity was actually very similar to what you would record in the wild. So that means that the animal sort of understood that he's moving in this environment to some extent. So yeah, so you could use some screens. You could use 3 highly curved screens put around the animal, then like commercial ones. It's you just need a solenoid valve, which is just a water dispenser, air puffs, and the laser tracking sensors. You body fix the animal, and yeah, you can have brakes on the ball. You can have the wheels on there. Okay, I'm not going to go into this. This is more of a software implementation, but it's also quite high level. But that's fine. Okay, so I trained the reinforcement learning agent on the first. I just put this slide to sort of convey that it's really easy to use. doom for these experiments. You can design your own maps. You can change the behavior of all kinds of objects. Like I changed the behavior of doors so that you don't have to press a button to open the door. You can just bump into it, with which I just removed a behavioral, necessary behavioral action from the experiment. And yeah, you can train all kinds of reinforcement learning algorithms on this. Whatever, we can talk about it later if you want. Alternative experiments. So what would be really interesting is if you could actually, after introducing incrementally these more and more complex maps to the rat, and it learns the maps and all that, how about just putting the rat right in the final map and just let the AI have time and just let it happen completely automatically. So you don't even have to design maps for the animal to learn navigation, learn shooting, but you just put the animal in there. And let's say you can have a heat map over the whole map, over the whole like Doom map. You can have a heat map that shows you at which point of the map, what is the performance of the animal at each point of the map. And you can recognize places where, for example, the animal is not shooting and there's a monster there, where the animal does very bad. And every time you expect the animal to do bad, you can have the AI come in and like show it the right action. So you can theoretically you can fully automate the training, but what I would say is that first you would want to go with this the simple case when you just engineer these maps out, so incrementally show the game mechanics to the animal and not just throw it in the final map. You can test your visual or auditory cortex stimulation. So okay. So let's say your animal learned to play Doom, right? And let's say you want to stimulate its visual cortex to see some sort of object. So in this case, you could make the animal see a monster. And there are different ways how you can check whether your stimulation was good enough to elicit a vision of a monster inside the rat's head. And one of them would be to record, you stimulate V1, let's say, of the visual cortex, and you stimulate subsequent, you record from subsequent brain areas like V2, V4, and then you check whether the activity of what you see in the downstream subsequent visual areas are similar to the visual pattern that you would have when the animal actually sees a monster. And if they're comparable, then you can claim that, okay, I actually stimulated a monster into the vision of the animal. But what if in this experiment, what you can do is actually behaviorally check whether it actually worked out. So, if the animal if the animal is effective and really good at shooting down these monsters, and you stimulate so that it sees a monster in front of it, then if the animal actually does the behavioral action of shooting, that's the point when you can believe that, okay, the animal actually thought that was a monster. So your stimulation is somewhat accurate. Okay, facilitate learning, augment memory. What I really want to say here is that games use all kinds of cognitive functions of these animals, and you can have the same environment. You can have the same VR setup where the animal plays different games and learn different tasks, and in those different tasks use different cognitive functions like planning, or learning, or what have you. And because you instead of being a hardware problem, now designing experiments became a software problem. You can do these all kinds of neuroscience research behavioral experiments inside this VR setup. Also, obviously, there are like other outcomes that could come out of this this experiment. But yeah. All right, we can talk about these anticipated challenges later, but I think I'm pretty much over time. Timeline, not that important, it's kind of rough. I have the references here for you. I think we're going to share this with you once we're done. And that's it. So let's start a discussion.
Great. Thanks a lot, Viktor.
Thanks a lot, man. All right. So should we proceed with the questions, if it's all right?
Sure. Let's go first with the questions that are in the Q&A. I see Paul is here. Is he still here? Yeah, Paul is here. I can do the question myself. Paul, if you want, you can just jump in as well. Because, I mean, you know, like hack nights are better done as a discussion. Here's Paul, allowed to talk. Yeah, so Paul, you can talk.
Cool. Thank you. Can you hear me?
Yeah.
Yeah, man.
Okay, great. First of all, thank you, Viktor, for that great presentation. And thank you, Firas and Guillaume. It's nice to see you guys again. It's been a while. Very excited to see you guys are doing the hack nights again. So that's super cool. I had a question for you, Viktor. Actually, I had a few questions, but I'll just ask the first one, and then other people can ask questions. And if there's more time, I can ask some more. But the question I put in the chat was just about the reinforcement learning agent, and I was just curious if maybe you already saw it, whether there's a chance that the rat will just become too used to the reinforcement and just rely on using that instead of actually learning the actions. So, what do you think?
Right. Yeah, that's a very good question. It is likely. I think it depends on how you select the times of the stimulation. So if it's very sparse, so if every time the animal doesn't do the right thing and you come to the rescue, that's the point when the animal can just adapt to just wait for the stimulation and not do the thing. But what you also have here is that if you do this more sparsely, so that okay, like in every run, let's say you constrain the number of times that stimulation can happen, like 4 times, and you only stimulate when you really expect the animal not to do the right thing, then I think you can go around that problem. Now, what's also but it's really okay. Yeah, what's another thing? These animals actually they are very much incentivized to do the right actions fast. So that's the thing. So let's say if the animal is stuck and that's the only time you stimulate, the animal just stands around. It's actually the animal, like for these VR experiments, they usually water restrict the animals. So for like 5 days, they get less water than they would actually drink, and they reduce their body weight to like 85 to 90% of their original body weight. And the animals are actually very incentivized to do the right action and do it fast, so they can get the reward fast, so they can drink. So if they have to wait around for the stimulation to happen, then they're probably not going to do it. But I mean, it's a rat. I don't know. There's no first principles that I can start from and derive.
Yeah.
whether they would or wouldn't.
Yeah, for sure. Yeah, no, that makes sense. I think you could. I mean, I think you can get around this, but that would be something. If I were running the experiment, I would be, I guess, maybe just mindful of that and how to apply the reinforcement. At which points would you actually do the reinforcement? Obviously, you can't do it right away. Otherwise, it's going to get too dependent. So, like, finding that timing might be an interesting challenge, I think.
Right. Yeah.
We have like a bunch of questions. Halim, you're here. Do you wanna go on and do the question yourself, or I'm gonna make you okay, Halim, you can talk, and if you want, I can just pass the question to Viktor as well. So yeah, Halim was asking, might the rat learn to enjoy the game later or without getting a reward? Because if that were to be the case, then we could observe why and how are we both humans and rats enjoying the stimulation? Yeah. under better how this phenomena happens and how it works to eventually learn to tame it?
Right. Yes. I think the answer is yes. So I think there has been some VR experiments where they initially used the reward, and at one point they stopped using any reward. Actually, while they were testing the animals, they completely stopped giving rewards, and they still were going around in these virtual environments. And I mean, who can tell? Is it addiction, or is it actual the joy of performing? Because once you start to do like complex tasks, that's sort of, well, I mean, that's a human behavior. I'm not really sure if I can extrapolate here, but once you do complex, teach them complex enough tasks, then they can get so that they use a lot of their cognitive capacity to play a game, and they understand when they win and when they lose, then they can start enjoying it. They can have this sort of, what humans have, this sort of flow state of like enjoying a game that are difficult enough, and you're good enough at it, so that you're completely fixated on it. So it could happen. That would be kind of interesting, and there has been research where they didn't give them rewards at the end. So I think it's possible. Yeah.
Yeah. Vignesh, who asked the question, he's not here anymore. He was saying, how does the rat perceive the reward and link it with the context of the game? And then there's another relevant question that is very much similar, which says, what would rewards be in an electrophysiological context? I think this is a very nice question, because most of what you were saying, it relies mainly on the motor cortex, and then
Yeah.
all these lists of things such as licking, blinking, and so on and so forth. They're all they're all behaviors that the rats do in the first place, and then you're detecting this, and then you're correlating these with other metrics. But then, like within the electrophysiological context, what would these rewards be?
So how would you stimulate the animal for it to understand to get a reward, or what do you mean by electrophysiological context?
I think, I mean, it's an
Stimulating
anonymous
dopamine
attendee who
neurons?
puts in.
Sorry.
Could be, but because I think they're just trying to understand the reward in terms of electrophysiological things, not in terms of something outside the animal. So how can you reward the animal immediately through stimulation?
Yeah.
Can I chime in for a sec? Sorry, I don't know if this is supposed to be an open discussion. I heard the question. I don't think this was the point of the experiment, but I think that you could do that if you just stimulate, the pleasure centers in the rat's brain. You could actually do that.
Yes.
But that doesn't seem to really be the point of the experiment. It's when you give the reward, the water or whatever, naturally the dopamine receptors or whatever will fire in the rat's brain. So you're kind of getting the electrophysical action through the behavior, not through direct stimulation of the brain. But it could be an interesting experiment to also try to do that, targeting specifically the rat's pleasure centers or whatever like that, that there could be a different take on the experiment maybe.
Right. Right. I mean, it's interesting because when you stimulate like what you call like the pleasure center, or you stimulate some dopamine neurons, these neurons have very different, they have a very sparse connections with the motor cortex. So let's say you stimulate some part of if you stimulate the whole pleasure center, you're gonna be fine, I guess. But you might stimulate parts that doesn't really communicate with that part of the motor cortex that, for example, does the nodding. But in general, you can say that yes, there's some sort of reinforcement learning that's happening in the rat, taking into the context. I mean, there's obviously going to be some trial and error here. There's going to be a lot of trial and errors where the animal just shooting in the air because it understood, well, when I nod, I get a reward. right? But it's not a thing. So it has to then at that point adapt and take the context into account, the visual stimuli.
There's Asmar who was. I'm gonna just read what he wrote. So he says, you have the issue of recording and stimulation overlap using electrophysiology, but if you tried viral approaches like photometry and optogenetics, you could have temporal precision.
That's okay. That's fine. I'm not an expert at that. I believe that. The thing is, I just want to make it as simple as possible. I would assume that those kind of procedures are more involved. So, and yes, you have like very strong stimulation artifacts, and there's way around that. There's a couple papers out there to like how do you take the residuals, all these artifacts out of the surrounding electrodes. And obviously it's not completely accurate. I mean, you can't go completely accurate with this. But yeah, but that's a good idea. I'm not sure if you would with optogenetics. Do you have optogenetics devices that you can have without fixing the head of the animal? Is that possible? I'm not sure. I'm not that up to date.
Me neither, to be honest. But the person who asked is not anymore available. So if they come back, they can definitely jump in. We have the last question from the questions that were put here. I'm just going to read it again. So it says, does the neural decoding have to be personalized models for each rat?
Yeah, that's a good one. Yeah. I would say that the decoding part can be, and because it has been done. It has been done from the motor cortex and the cerebellum, and you need a couple hours of recordings, and it's done. So it's you can do it. Obviously, there's this plasticity going on. There's what is it? The functions of these neurons change over time, and it's very. I think from the machine learning perspective, it would be a very interesting study to find some sort of inductive bias that you build into your let's say into your neural network, so that it's able to somehow generalize between animals. And what you can do, for example, for stimulation, is that you learn that okay, these electrodes are more likely, and you use that. These electrodes are more likely to stimulate a certain muscle, and then you use that as some sort of prior for training a new model on a new animal. So there are ways to somehow do this. I don't think for decoding specifically it's necessary, because it's relatively, although it seems like it's complex to decode in which direction the animal intends to move, but from previous VR experiments, it seems pretty easy. You can fit a linear regression model on it, and it's just going to learn from an hour-long recording. So, yeah. But it's interesting. It would be really interesting to do that.
If I can add on to that, just I don't know about rats very well, but I do know that in the brain gate experiments where they have human subjects that are implanted with Utah arrays, they actually were able to get them to perform like a cursor pointing task within just like 5 trials. They got like super good accuracy. So I think there's been a lot of improvement on that. And I don't know specifically what they did to get that sort of performance, but I'm assuming if that they can do that in humans, then it should be pretty easy to do that with rats as well.
Yeah, I think so. Yeah, right.
Yeah. If there's no other questions, I actually had some more questions I can
Sure, go ahead.
Okay, yeah. Cool. Yeah, so I thought it's a very cool experiment. I was curious about what you said kind of towards the beginning about basically changing the visual input. Oh, what just happened? Oh, okay. panel was cool. So yeah, just changing the visual input to match kind of the rat's own way of seeing, because I would almost anticipate that you would want to do the opposite, kind of increase the resolution, because the rat's visual system itself is kind of degrading the visual input. So wouldn't you want to
okay, yeah, no,
make things like, for example, and also in those slides where you showed the previous virtual reality experiments, you notice it on the walls, they have this like bright black and white, highly visual contrasting pattern. I suppose to account for the rat's kind of poor visual acuity and stuff like that. So I would thinking that may be a way to go, or I don't know if they tested that out and came up with some sort of optimized designs in those previous experiments. It might be something to look at.
No, so what I meant in the beginning is not to, so I wouldn't Gaussian blur the image for the rat. I just want to somehow like visualize it, like how much the rat, what amount of information the rat could see from the game, right? I don't want it to, I obviously don't want it to make it worse than it already is.
I see. Yeah. Okay, I guess I misunderstood what you were saying. So that's basically just to try to understand, are the things going to be visible to the rat? Cool.
Yes.
And kind of on that same point, I was thinking about that. How can you get the rat to better see the demons and stuff? It's good that you can customize those characters and stuff, because I was thinking, you could either try putting like the black and white bars on the demons to make them more visible, or even perhaps, I don't know if this would work, but I was like thinking maybe you could customize them to be like something that the rat actually dislikes normally, like make them look like cats, or maybe like other rats or something like that, just to get it to be more likely to act when it sees those things. But that might be kind of difficult. But
yeah, no, it's actually not difficult. There's a version of Doom where you have nyan cats instead of monsters.
Yeah,
that's cool. And actually, you could do like in Men in Black, when the protagonist is thrown into that field, and he has to shoot to different either monsters or save the girl, So you could put like the demons or the cats in order the rat to shoot them, and then you could add another rat and give him a reward if he doesn't shoot the rat. It's just an idea,
Yeah, no, that's the thing. You can do all kinds of things.
No, definitely.
Yeah, and what you said about the like changing the it's called in Doom in these games sprites of the enemy. So you can, for example, what I was thinking about is when we talk about 1 cycle per degree, we mean at the maximum contrast. So you have 2 black lines, and in between you have white. So that's the assumption there. And as you decrease the contrast, so your lines become more whitish, the visual acuity is decreasing. So what you could do is, like, I think the simplest one that still remains true to the game is to just have like a halo effect around the monster, just like a white stroke around the monster, so that it's more visible to the background, which is usually darker. But yeah, I mean, you can introduce. Now the problem with cats is that if you think about it, rats are very what is it? They are not they're not aggressive animals. They are very much they would rather run away than anything else, right? If they're very risk averse. So if you show a cat, shooting might not be the right, I don't know, because that one starts to play with the actual, what the rat understands of cats.
Yeah.
And there's nothing that the rat can do that it learned evolutionary that's going to shoot down a cat.
Yeah, for sure. Also, I suppose the cat would have to be a lot larger than the rat in the image, which could make
that's true. Yeah, that's also.
But I wonder what is a rat's natural response when it meets another foreign rat? Do you know?
When it meets another rat?
Yeah, are they territorial at all? Do they get along? If say one male rat were to encounter another male rat in the hallway, what does it do?
Well, I'm I'm somewhat educated in rat behavior, but what I can, but not, I'm not a complete expert. What I can say is that it varies a lot, so you don't really know. There's usually a power play that goes on, but it also depends on the environment, right? If you have a very playful environment, like low stress, then there's more play than aggressive behavior going on. If you have females around, that changes the equation. So there's a lot of variables. So you can't really in general say that, if two male rats meet, what's going to happen.
Right.
In this case, they wouldn't meet. What you could do is that they can, you could have social experiments. Actually, that's again, yeah, that would be pretty interesting, just to project all the animals into VR and see what they do in there with each other, maybe. But you can already sort of do that in a cage, to some extent. What could be also interesting is just to let them play multiplayer, but then they wouldn't understand that that's another rat. They just understand that that's something that has to be shot. But yeah. Any other?
Yeah. Like from the questions, but I mean, I'm sure Guillaume has a lot of things to be talking about. He didn't have any questions yet, and me too. Guillaume, you want to go first?
Okay, as you want. I just have, I don't know if it's a simple question, but when you have been developing this platform, let's say, I guess at some point you have come up with some ideas of what could come after its implementation. So if it ever is successful, what could be the impact of such technology being applied into society or people in general?
Yeah, and even I could just add one thing, is that like, how does that expand the whole neurotechnology space, right?
All right. So, okay. So I think there's two parts here. One of that is what I've mentioned in the presentation, is that it gives you some sort of platform that you can have more and more these neuroscience experiments without changing much of the hardware. So it stays simple, and you can record and decode, decode and stimulate all kinds of cognitive functions, and establish neural maps and causal connections and whatever you want. Now that is one. The other one is it ties in here, is that whatever device you use to decode, like decoding is, I might go a little bit far with this, but I think decoding is solved. Stimulation is the part of the equation that's very difficult, and it has, it's like, it just has so many layers of like, and you also have to do it online. You can't just do it offline. It's very complex. You can't fit like an analytical model on what's going to happen in the brain if you stimulate with X, Y. You have to record the responses, and you have to make sense of it. So this is like a research environment where you can test all kinds of like stimulation and decoding paradigms. And what even comes, I think, after that, is that if you don't want to bootstrap from the motor action of the animal that you assign in this example to shooting, what you actually want to build this auxiliary neural interface that I call this, but it's basically just a group of neurons that you prime to be the neural circuit that should initiate the shooting action. If you can build that like this is a kind of environment where you can sort of test it out, right? How should I stimulate? What parts of the motor cortex can I stimulate? Can it be just a very simple stimulation sequence? Do I have to go and record downstream neural areas or surrounding neural areas to figure out whether my stimulation actually had some network effect. Like all these questions are not that much figured out, and well, this is an environment where you can test these things out. And what's also what I haven't mentioned is that what if you can you have a map, or you have an environment where the rat has to let's say run around. It has 3 paths to take, and those paths at the end they connect, and they have to pick up all the objects on those 3 paths. And then in the beginning they have a decision which basically which can constitute as a planning decision. If they gone through the map enough times, sort of understand that, okay, now I'm going to start from the right. I'm going to start go to the right, and then go to the middle one, and then go to the left one. Or I start from the left, and then I go to the right one, and then to the middle one. And that's some sort of planning that has to happen there after the animal went through these environments enough. And can you actually decode that plan? You know, can you actually anticipate what the rat's going to do next? Can you change that plan? Can you stimulate the rat to choose the right path instead of the left path in the beginning? But this is, again, it goes back to, you know, being able to design these experiments very easily. But what I think is the offshoot is just to build these auxiliary neural interfaces, and what we can use for even for humans to, like, let's say, not just to play games, like to interface, you know, software in all kinds of ways without actually, you know, me needing to think about, okay, now I'm moving my hand to the right, and the cursor on the screen should move to the right, right? Like that. Instead of that, I just select a group of neurons that should, let's say, fire when I move to the, I mean, I'm going to be very simplistic with this argument, but you can have, let's say, different groups of neurons that tune to certain degrees of cursor movement, right? And you can prime those neurons through stimulation. And that is the hard part, and that has to be researched. And I think this is an environment where you can do that. You can prime these neurons to move the cursor into a certain direction, and then inhibit all the other groups of neurons, so that it's clear that, you know, there's a certain direction that's selected. But, you know, one could say that this experiment can be done with primates, to just moving cursors. You know, you can do this with like other different experiments. It's possible. But I think there's just a lot of cognitive functions that you can cover with the same experimental setup, and that's basically what it is. And everything that comes out of that is what the what's the benefit.
That's cool. I think that at some point, like there is definitely a drive to create like a smaller and more precise stimulation devices. So yeah, well, that's basically what Neuralink and all these companies are. So who knows what will happen in 10 years, you know?
Yeah, that's another thing people were asking about. Morgan is here as well. Morgan, would you like to say something?
Well, yeah, just to add to Victor's point, and great presentation, super interesting topic. I'm really glad that I got this. But I just dropped a link to this kind of review article, mainly just for this this little quote, or, you know, what Anne Churchland points out at the beginning here, which is that, you know, what was really kind of like made this a landmark study back in 2010 is that, like, the visual activity that they're recording is completely different if the animals are in control of their movement, you know, and so, you know, it's like what they're seeing is qualitatively different activity, even though in a sense they're getting the same visual stimulation, right? And that to her was like, I mean, this was her point, which was just like, you know, my God, we've been kind of doing things wrong, you know, and that, like, these more kind of active tasks, or, you know, making the experiment live, actually is changing the brain activity. And like, honestly, we want to understand that live brain activity as opposed to the immobilized, anesthetized activity that is, you know, pretty common in animal research. You know, this idea that like we anesthetize because we can do that with animals and we can't do it with humans, when in fact, what we really want is the live activity. You know, we want to be doing the same experiments that we're doing in humans in these rats, because like that's actually the you know, brain activity we're interested in. Right. And so, you know, even though it's much more difficult, it involves, you know, a lot more equipment and a lot more. It's funny because right before this, I was actually speaking with Marius Klug in Berlin at the brain, you know, I forget it's the mobile brain body imaging lab, right? And this is,
yeah, was that Klaus?
It wasn't Klaus. I mean, Marius Klug.
Oh, and yeah, okay.
He's pretty active on Slack, and you know, in some ways, like you know, Victor's talking about like, yeah, I want to do in rats what Berlin's doing in humans, you know. and I mean, you know, obviously, you know, it's the invasive recordings is what makes it, you know, I mean, that's something that we can do more at scale, obviously, right, with animals than maybe, you know, I mean, I think Paul's example with BrainGate is super interesting too. But like, yeah, we can do this at scale, and certainly we can do this at more accessible costs, hopefully.
Right.
But yeah, I mean, it's a really important platform that you know, is changing what we're getting, and we really need to understand this new these results as opposed to anesthetized results.
All right. Yeah. Now it's like, and there's just to tie into that, there's like even more layers to this. So what they figured out that even in these VR environments, when you have a head fixed animal, their visual responses is again completely different from a body fixed animal.
Yeah.
So there's, you know, it's like, yes, you should have this interaction with the environment at least, and somewhat it should be authentic, and you shouldn't constrain the animal too much, because yeah, it ruins your signals.
Yeah. I mean, you know, and obviously we have to deconvolve all of this, and you know, and it maybe requires doing it in a couple different ways. But what we know we're actually interested in is the freely moving, you know, activity, and you know, freely moving naturalistic activity, and you know, so doing VR with rats is like trying to create that under laboratory conditions, you know. And anyway, so it's like, it's, you know, some of the technologies that we use in kind of, you know, I don't want to say toy problems, but certainly like consumer applications with but we're using lab streaming layer. Lab streaming layer was developed to handle, you know, multiple data streams from, you know, body imaging together with eye tracking, together with EEG, together with, you know, anything else they could add, synchronized timing, you know, and yeah, so super great to see this. And yeah, I'm curious how, you know, how open are these experiments? Like, you know, will we be hearing more about how this is progressing, how this work is progressing?
Well, so what I did here is that I went through all the, what I thought is like the different ingredients of this experiment, right? And I tried to figure out whether it's possible and how easy it is. And that's where we are at now. So I can't really speak from Feinstein's perspective. It's not something that we often do, like training rats to play video games. So we'll see if I can get them. I mean, this was also just like a way to like get this information out there, and if someone is interested in this, they it's on their map, so they know that it's possible, and I can share all the research I've reviewed.
I'm sure there's a lot. We're just 5 minutes away. So there's a question that a lot of people were asking, and I was keeping it till the end because I know it's like a bit off what you were saying specifically. That yesterday or 2 days ago, Elon Musk was saying that they already put in a monkey with a BCI to play video games. So I don't know if you saw this. What do you know about it, and then what do you think about it?
Yeah, I've heard the Clubhouse interview or talk. Yeah. So I mean, that's pretty cool. I don't know what else to say. I've actually interviewed a Neuralink. I can't really talk anything about that or what I know what they do. Well, what I can say is that there's some hyper smart people there that I think if they set their mind to do something, they're gonna do it. So I think it's cool to start with that. It's always making monkeys play games. I guess that's easier than to make them do more mundane tasks. So that is just a very cool like first step that's even cool for us humans. So yeah, way to go.
Yeah, good stuff. By the way, Morgan, I was having a conversation with Klaus from Bmobile, the lab in Berlin, and then he might be on a talk with us sometime soon. I mean, I need to talk to him about that as well. But he's definitely, Klaus is definitely on the list. I had like some conversations with him. Super cool guy.
That's awesome. That's awesome. Yeah, and I don't know if you saw that. Michael X. Cohen is going to be speaking there tomorrow. Yeah. And it will be, I think, at a better time for Europeans than in San Francisco, but it sounds cool.
Definitely.
And just I posted this on Slack, but Deep Lab Cut, they did a the Society for Social Neuroscience did a tutorial this past Sunday, and and now if you can do a freely moving animal, but I talked to Marius a bit about this in terms of like, what's comparable research software for humans for this kind of thing, and he said, at this time they're still kind of using Steam VR, and things that are built into Steam VR and things that are built into Unity. To pull out this kind of stuff, but curious, another thing we can add.
That's like the. No, just posting the link here. It's the mouse motor lab, right? Oh, we just posted the same thing.
Yeah.
Great.
Oh, yeah. Oh, okay, good. Yeah, go.
Perfect.
Yeah, that's very relevant with the, like, even if if you want to record and you want to classify whether the rat opens its mouth, there's probably a way to go. Using Deep Lab Cut, I mean, and all kinds of like, because as far as I understand, they basically just use some computer vision and neural networks to you give them like a small amount of training data of like, okay, this is now an open mouth and this is now not an open mouth, or this is now how the hands of the rat is positioned, and then it just learns pretty fast on those training data, so you can use that classification later. Yeah, it's pretty cool.
So yeah, I think we just got to the end. These were like really intense and hardcore 2 hours. Really enjoyed it. I definitely want to thank everybody who joined. Of course, Victor and Guillaume for setting this up.
What is? Thanks a lot to thanks to Victor. He's the one who was talking.
Thank you guys for getting me.
Any last words, Victor?
Sorry.
Any last words before closing?
Contact me if you want to do this research. Just that.
Sure. Yeah, the thing is, I mean, for you as well, this was streaming live on YouTube, and it's going to stay there. And definitely there's your information in the presentation. So if anybody wants to revisit that as well, and I'm sure some people here are already on Slack, and then they have access to the event on Meetup, which has your information. So
Nice. Should I share the presentation or?
Maybe you want to
Yes.
show just the last slide, which has your contact, but there's already people who say that they're gonna contact you as well. Morgan, I'm sure Morgan will.
All right.
Okay, so that was great. Thanks everybody for joining.
Thanks a lot. See you soon, okay? Take care.
Ciao.
Bye-bye.
Bye-bye.
Bye.